Hello, dear students. Welcome to the second session of our online tutorials in chemistry for class 12. In the first session, we have started our discussions on solutions from Unit 2. And today we will continue with the same, that is Unit 2, and we will see some more topics from these solutions. But before we start that, I will first give you the answers of the two questions that I asked you to try at home in the first session. So the first question, I asked you to find the mass percentage of glucose in a solution in which 10 gram of glucose is dissolved in 100 gram of water. The answer for that one is 9.09 mass percent. The second question was to find the mass percentage of benzene and carbon tetrachloride in a solution in which 22 gram benzene is dissolved in 122 gram of carbon tetrachloride. There, you are asked to find the mass percentage of both benzene and carbon tetrachloride. So, mass percentage of benzene in that solution will be 15.27%, and the mass percentage of carbon tetrachloride will be 84.72%. As I told you in the previous class, to find the mass percentage of any component, you divide the mass of that component by the total mass of all the components in the solution and finally multiply by 100. So please check your answers again. Now, I want you to go back to what we discussed in the previous class again. We discussed about 6 methods of expressing concentration of a solution. Now, in the third method that we discussed, to find the mass by volume percentage, I have mentioned that the mass by volume percentage of a solution is given by mass of the solute divided by volume of the solvent. I want you to make a correction there. Mass of the solute will be divided by volume of the solution, not by volume of the solvent. So mass by volume percentage of a solution is given by mass of the solute divided by volume of the solution. Please make that correction there. Now today, we will discuss about solubility. Solubility refers to the maximum amount of any substance that can be dissolved in a given amount of a solvent at a given temperature and pressure. So how much of the substance can be dissolved in the given amount of the solvent, that will determine its solubility. If we can dissolve a huge amount of the substance, then its solubility will be high. Whereas if we can dissolve only a small amount of the substance, its solubility will be low. I want you to try this simple activity at home. You take 2 glasses of water, and in both glasses, you take 100 ml each of water. Then in these 2 glasses of water, you put sugar in one glass, and in the other glass you put sodium chloride, that is the table salt that we take. See how much of each of these solids can be dissolved in the same 100 ml of water. Try to find out which will dissolve more. If you can dissolve more of sugar, that means its solubility will be higher than that of the salt. However, if you can dissolve more of the salt, then its solubility will be higher than that of the sugar. That's a very simple assignment that you can try at home, and that will help you to understand this concept of solubility better. Now, there are 3 factors that affect the solubility of a substance in a solvent, or the solubility of any solute in a solvent. These are nature of solute and solvent, temperature and pressure. Now we will discuss about the effects of these three factors on the solubility of solids in liquids as well as on the solubility of gases in liquids. In these two types of solutions, we will discuss the effects of these three factors. First, let us see the first factor, that is nature of solute and solvent. If we have a solution in which a solid is dissolved in a liquid, you will find that a given solid cannot be dissolved in any kind of solvent. You will be able to dissolve that solid in only certain kinds of solvents. Likewise, a given solvent will be able to dissolve only certain kinds of solid in it. It is found that those solids in which the intermolecular forces of attraction are similar to that of the forces of attraction in the liquid, that is in the solvent, only those solids are found to be soluble in that particular solvent. That means polar compounds or polar solutes, they are soluble in polar solvents. Non-polar solutes, they are soluble in non-polar solvents. We cannot dissolve a polar solute in a non-polar solvent. For example, sugar or sodium chloride, we can dissolve in water very easily because these are polar compounds. Sodium chloride or sugar, all of these are polar compounds. They are soluble in polar solvents like water. But these polar solids, they are insoluble in non-polar solvents like benzene or carbon tetrachloride. On the other hand, if we take non-polar compounds like anthracene or naphthalene, we can easily dissolve this in the non-polar solvents like benzene and carbon tetrachloride. So we can say that like dissolves like. A polar solute can be dissolved in a polar solvent, whereas a non-polar solute can be dissolved in a non-polar solvent. This applies to solutions in which gases are dissolved in liquids also. For example, oxygen is very slightly soluble in water because oxygen is a non-polar compound. Water is a polar solvent. But if we take HCl gas, vapors of HCl, we can dissolve this easily in water because HCl is a polar compound and water is a polar solvent. So for gases also, the nature of solute and solvent plays an important part in the solubility. The second factor that we have is the effect of temperature. Now, temperature also plays an important role on the solubility of solutes in solvents. If we have, once again, a solid dissolving in a liquid, we will find that if the solid dissolves in the liquid endothermically, that means when the solid is dissolved in the liquid, if heat is absorbed during the process, then increase in temperature will increase the solubility of the solid in the solvent or the solid in the liquid. But if the dissolution process is exothermic, that means when we dissolve the solid in the liquid, if heat is given out, if the process is exothermic, then we will find that increase in temperature decreases the solubility of the solid in the liquid. Likewise, when we try to dissolve a gas in a liquid, temperature also plays an important role again. Increase in temperature will decrease the solubility of a gas in a liquid. Why? Because the dissolution of a gas in a liquid, once again, is an exothermic process. It is quite similar to that of condensation. You have learned that condensation is the process in which vapors turn into liquid. So when we have a gas dissolving in a liquid, the process is quite similar to that of the condensation process. And in this process, heat is evolved. The process is exothermic. Therefore, for gases dissolving in liquids also, increase in temperature will decrease the solubility of the gas in the liquid. Finally, the third factor that affects the solubility of a solute in a solvent is pressure. Pressure, when we change the pressure, solubility of a solid in a liquid is hardly affected. That means change in pressure has no significant effect on the solubility of a solid in a liquid. Why? It's because solids as well as liquids, they are highly incompressible. They are very less compressible, that means. So change in pressure has no significant effect on both solids as well as liquids, and therefore solubility of solids in liquids is also very slightly affected by change in pressure, or it's not affected by change in pressure. However, if we have a gas dissolving in a liquid, gases being highly compressible, their solubility is very much affected by the changes in pressure. Now, let us see a liquid in a container in which we want to dissolve a gas. When we apply pressure on the gas, the gas gets compressed, and when it is compressed, the volume decreases. So the number of molecules of the gas per unit volume increases. The volume decreases, number of gas molecules per unit volume increases. Not only that, the number of molecules, the gas molecules that strike the surface of the liquid, and the number of molecules trying to go into the solution also increases. And due to this, increase in pressure will increase the solubility of the gas in the liquid. Now, this relationship between the solubility of a gas in a liquid, that means how much of the gas is dissolved in the given liquid by change in pressure, by changing the pressure. That relationship between pressure applied on the gas and the amount of gas dissolved is given by a law which is called as Henry's law. Now, according to Henry's law, at any given temperature, the mass of gas dissolved in a liquid is proportional to the pressure of the gas in equilibrium with the liquid. So, the more the pressure that is applied on the gas, the more of it that gets dissolved in the liquid. So, once again, Henry's law says at any given temperature, the amount of any gas that gets dissolved in a liquid is proportional to the pressure of the gas in equilibrium with the liquid. Now, this law can be stated in another form, according to which pressure of the gas, the partial pressure of the gas is proportional to the mole fraction of the gas in the solution. So, partial pressure of the gas, let us write P, is proportional to the mole fraction of the gas in the solution. the pressure applied on the gas is proportional to its mole fraction in the solution. So P will be equal to a constant of proportionality, which we will write as Kh into this mole fraction. The constant of proportionality that we use here, Kh, is called as Henry's law constant. Now it is found that the value of Kh is different for different gases at the same temperature. So this implies that Kh, the Henry's law constant, is a function of the nature of the gas. That means at a given temperature, different gases will have different values of this constant depending on their nature. There is another law apart from this Henry's law, which is called as Raoult's law. This Raoult's law, it gives us a relationship between the partial vapor pressure of a component in a solution and its mole fraction in the solution. So in its general form, Raoult's law can be stated like this. Raoult's law, in its general form, it states that the partial pressure of any volatile component in a solution is proportional to its mole fraction. So if we have two components A and B making up a solution, according to Raoult's law, the partial pressure of the component A, let us write PA, will be proportional to its mole fraction. So PA will be proportional to the mole fraction of the component A. Likewise, for the component B, the partial pressure of this component B will be proportional to its mole fraction, that is XB. For liquid-liquid solutions in which both the liquids are volatile, we can say that the partial pressure exerted by each component in such a solution is equal to its or proportional to its mole fraction. Now, if we have this component A, if we consider this component A, partial pressure of the component A is proportional to its mole fraction in the solution. So the partial pressure of A will be equal to a constant multiplied by this mole fraction XA. In this case, we will write PA naught. Now this constant of proportionality, its value is found to be equal to the vapor pressure of this component A in its pure form. That means PA naught here is the vapor pressure of component A in its pure form. Likewise, for component B also, we can write vapor pressure of component B equal to vapor pressure of the pure component B into its mole fraction XP. Now, Henry's law says pressure of a gas dissolved in a liquid is proportional to the mole fraction of the gas in the solution. So we got P pressure of the gas equal to a constant kh into x. From Raoult's law, we have pressure of any component A in the solution equal to pressure of that pure component multiplied by its mole fraction. Now, in both cases, we have pressure of volatile components here. A gas will be a volatile component because it's in the vapor phase. In Raoult's law also, we are considering the partial pressures of volatile components also only. So these are partial pressures of volatile components, and these are equal to certain constants multiplied by the mole fractions of the components. So the only difference between these two here is that of the constants that we use to multiply the mole fractions. Therefore, this Raoult's law is said to be a special case of Henry's law, or a modification of the Henry's law. Now, solutions which obey this Raoult's law, that means for which pressure of a component is equal to pressure of that pure component multiplied by its mole fraction, such kind of solutions are called as ideal solutions. Now, such kind of solutions will obey this Raoult's law at any concentration and temperature. So PA will be equal to PA net into XA for a component A, and for the component B, PP will be equal to PP naught into XP. However, we will find certain solutions in which these are not equal. PA may not be equal to this, PP may not be equal to this product. In other words, PA may be greater or less. PP may be greater or less than this product. Such kind of solutions are said to be non-ideal solutions, and they do not follow Raoult's law. So based on this, we get two kinds of solutions: ideal solutions and non-ideal solutions. Ideal solutions are defined as two solutions which obey Raoult's law at all concentrations and temperatures, and non-ideal solutions are those which do not obey Raoult's law. So once again, if we have a component A in a solution, and the solution is an ideal solution obeying Raoult's law, then PA, the pressure of the partial pressure of the component in the solution, will be equal to the pressure of the pure component multiplied by its mole fraction. So we can write PA equal to PA naught into XA. For ideal solutions, enthalpy of mixing, delta H of mixing, is found to be equal to 0, and volume change, delta V of mixing, is also found to be equal to 0. So not only is the vapor pressure of the component in the solution equal to the product of vapor pressure of the pure component and its mole fraction, enthalpy of mixing is also equal to 0, and volume change of mixing is also equal to 0 for ideal solutions. However, for non-ideal solutions, this is not equal. Delta H of mixing, that is enthalpy change of mixing, is also not equal to 0. Delta V of mixing is also not equal to 0 for non-ideal solutions. So if we see the non-ideal solutions, we get two cases where vapor pressure of the component is either greater than the product of vapor pressure of the pure component multiplied by its mole fraction, or where the vapor pressure of the component is less than the product of its vapor pressure in the pure form multiplied by its mole fraction. Those solutions in which vapor pressure of the component in the solution is greater than the product of these two, they are said to show positive deviation. Those in which the vapor pressure is less than the product of these two, they are said to show negative deviation. Now the question is, why do some solutions show positive deviation? Why do some show negative deviation? Why don't they obey Raoult's law? Or why is vapor pressure of the component not equal to the product of vapor pressure of the pure component multiplied by its mole fraction? Let us go back to ideal solutions again. For ideal solutions, for any component A, vapor pressure of that component will be equal to the vapor pressure of the pure component multiplied by its mole fraction. Now, in this kind of solutions, we will find that the solute-solvent interactions, that means the forces of attraction between the solute molecules and the solvent molecules, is quite similar to the solute-solute interactions and the solvent-solvent interactions. Let us take an example of a solution where we have a solute B dissolved in a solvent A. Before we mix these two to make a solution, the solute itself will have this kind of interactions, BP interactions. Let us take an example to understand this better. Suppose we have NaCl dissolved in water. NaCl is the solute that is dissolved in the solvent water. Now, the interactions between NaCl molecules, before we put NaCl in the water, in the solid NaCl, before we put it in the water, the interactions between NaCl molecules, let us represent by this BB, B to B interactions. And in water also, molecules of water will have certain interactions between them. Let us represent that by AA interactions. So AA represents the interaction between the solvent molecules. BB interactions represents the interactions between the solute NaCl molecules. Once we put NaCl in the water, a new interaction occurs between solute molecules and the solvent molecules. Let us represent that like this, A to B interactions. These are called the solute-solvent interactions. These are the solute-solute interactions. These are the solvent-solvent interactions. If these interactions, solute-solvent interactions, are similar to solute-solute and solvent-solvent interactions, then we will get ideal solutions. That means in such kind of solutions, BA will be equal to product of BA naught into XA. In such solutions, will obey Raoult's law. They are said to obey Raoult's law. But let us take another case where these AB interactions are not similar to this AA or BB interactions. Let us say AB interactions, the solute-solvent interactions are greater than the interactions that we find in the solute as well as in that of the solvent. If these interactions are stronger, that means they cannot be broken down easily. The molecules cannot be separated easily in such a case. So molecules going into the vapor phase will be less in such cases. If less number of molecules go into the vapor phase, then vapor pressure gradually decreases. So if solute-solvent interactions are stronger than solute-solute or solvent-solvent interactions, then we will get a case where vapor pressure is lowered, and therefore this PA will not be equal. It will be less than PA naught into XA. On the other hand, if AB interactions are weaker, if these are weaker than BB and AA interactions, then the weaker bonds can be broken easily. That means this can be separated from each other easily. More of molecules will go into the vapor phase, and therefore vapor pressure will increase. So when the vapor pressure increases, PA becomes greater than the product of PA naught and XA. As I mentioned before, those where the vapor pressure becomes lower or less, you will show negative deviation from Raoult's law. And those for which this vapor pressure is greater, they are said to show positive deviation from Raoult's law. Now, there are certain properties of solutions which depend only on the number of molecules of the solute, but are independent of the nature of the solute. Those kind of properties of solutions are called as colligative properties. There are 4 properties of solutions which are called as colligative properties, and as I said, these are properties of solutions which depend only on the number of moles of the solute but not on their nature. The first colligative property is relative lowering of vapor pressure. Then the next one, we have elevation of boiling point. Then third colligative property is depression of freezing point. Then finally we have the fourth colligative property, which is osmotic pressure. These are the 4 properties of solutions which depend only on the number of moles of the solute and not on their nature, and these are called as colligative properties. In the next session, we will be discussing in detail about these colligative properties. So before we come to a detailed discussion about these colligative properties, please try to remember what are colligative properties and what are the 4 colligative properties of solutions. We will discuss more about this in the next session. So till then, take care and good luck. Thank you.